Hello, everyone. Welcome to the next joint meeting of Washington Quantum Computing Meetup and Warsaw Quantum Computing Group. My name is Paweł Gora. I'm a leader of the Warsaw Quantum Computing Group, and I will be a moderator of this meetup together with Karim El-Safti from Alexandria Quantum Computing Group. And today we'll host a great speaker, Ben Jaderberg from University of Oxford, and he will give a lecture titled Quantum Self-Supervised Learning. So Ben, first of all, thanks for accepting our invitation. It's our pleasure.
My pleasure.
It's a great, very interesting topic, so we hope that it will be very successful meetup. So just information to all the participants. So first of all, this meeting is recorded, so hopefully there will be video recording published on our YouTube channel later. And also, if you have any questions during the meetup, during the lecture, please just post your questions on our chat, and at the end there will be a Q&A session. So we'll ask these questions. So before we start, let me just also mention that we are also going to organize a few more interesting events soon. So for example, on 10th of July, there will be another joint meeting, the lecture Quantum Computing in Cargo Load Optimization. So sounds very interesting as well. And later on 24th of July, explaining circuit mode of quantum computing as if it occurred in an escape room game. So I think that we can start now. So I will just stop sharing my slides, and Ben, the Zoom is yours. So welcome once again, and we can go on.
Great. Okay, so can you see my slide okay? Full screen and lovely?
Yes, we can see.
Good. Thank you very much for the introduction, and also for you're the first person in a while to pronounce my surname correctly, because in England everyone says Jaderberg, but as you said, it's Jaderberg. It's a Swedish name.
Great.
So no, thank you, and thank you everyone who's here for lending me some of your time on a Saturday. I understand, and I appreciate you come to look and to learn about what we're doing. And so I'm talking today about work that we put on the archive just a few months ago. So I should introduce myself. I'm Ben Jaderberg. I'm a third-year PhD student at the University of Oxford, very much studying quantum algorithms for near-term quantum computers, and sort of what can we do realistically, maybe in the next 5+ years. And so if you're interested in the work, then the archive link to the actual paper is down here. And also just last week, we released the code as well for people who want to reproduce. I should say that I guess it's a mixed audience, so maybe people in academia and enthusiasts. The talk is aimed somewhat at a academic level, but there'll be plenty of time. It's only 20-30 minutes, plenty of time for questions. Please ask any question, and nothing is there's no such thing as a stupid question, as they always say. So I hope it will be clear and you can understand it. So the first thing I want to start with you guys is this graph. And what the graph is showing is, in the last decade, the accuracy of the best performing computer vision models on ImageNet, which is a very famous database of pictures of everyday things like cars and birds and cats and things like that. And I want to show this graph because it looks magnificent in some ways. We have, in the last decade, essentially gone from a position of having barely over 50% accuracy when trying to recognize what's in the ImageNet database to over 90% as of the best performing models. And so in some ways, this is really a phenomenal achievement. But what I want to ask you here is, what is wrong with this graph? What is wrong with the progress that's being made? And the answer is that all of the best performing models are learned through supervised learning, which is incredibly, it's kind of the first type of deep learning that was done. And this involves human annotations of the images. So of course, someone has to physically go through 50,000 images and label them as cats and cars and dogs. And whilst this will always give us the best results in some ways, it's the least scalable way of doing computer vision and deep learning. And if we talk about what is a modern data set, a lot of these data sets are 10, 20 years old. Modern data set is like, all of the images on Facebook, for example, and there are 350 million images uploaded to Facebook every day. And for good or for wrong reasons, a lot of tech companies, what you want to do really is, can we classify everything on Facebook, everything on Instagram, for good reasons as well, maybe spotting things like modern slavery or abuse and things like that. And so as I mentioned before, the state-of-the-art models are at the moment always supervised learning. And so the very famous example is this so-called MNIST dataset from the sort of 1960s, 70s, which is handwritten digits. And you have to try and build a computer vision model that will guess what digit is being displayed. And then we have other types of learning, such as unsupervised learning. And this is kind of more like clustering algorithms, finding patterns. So the example I give is principal component analysis, PCA, which is often used in the financial world, for example, to try and spot correlations between different stocks and shares. But it's not actually classification, it's more finding patterns. And then what I want to talk to you about today is a thing called self-supervised learning. And it's a fairly, well, it's not a new idea. The idea was conceived in the 90s, but like many things in deep learning, it's only really come to fruition literally in the last year or two, because GPUs and computers are powerful enough that we can actually do these type of learning. And what self-supervised learning is the idea that you have your data set unlabeled. There's no need for human labeling, but our model is going to automatically generate its own class labels by manipulating the data set and use this to learn. And if that doesn't make sense, then don't worry, because I'm going to explain how we do it. And as I said before, this idea is highly relevant for modern data sets where you have millions of images, which are growing all the time. And you also are not restricted as to what the content of your image might be. There's no, everything in life can't be brought down to cats and dogs and cars. And self-supervised learning doesn't require any labeling at all. And so if we talk about self-supervised learning for images, we have this algorithm or this idea called contrastive self-supervised learning. And I'll try to explain how it works roughly. And it comes from this original paper that I've got cited at the bottom. So barely only a year old, this idea is. And as soon as I read the paper, we decided like it'd be amazing to try and do a quantum version of this. So anyway, so what we do is, for all of the images that we have in our data set or in our batch, because typically you turn the data set into batches, we actually are going to create two different augmented views of each image. So in this example here with the plane, this is our base image, and then we're going to create two augmented views, which involves basically randomly cropping, rotating, zooming, and changing the color of the image. And so for every image, we have two augmented views. And we're going to pass each of these augmented views through our architecture, which I'll get onto later. But most importantly, we have an encoder neural network. So something which is going to turn this image, this bunch of pixels, into a vector which represents the important features of the image. And although it's not very important necessarily, but there's also a second neural network we have called the projection head, which is, if you're interested, I can talk in more after, but it's essentially an optimization that you actually don't want to apply your loss function directly on the final layer. But by all means, focus on the idea that our architecture is turning images into vectors, into encodings. Okay, so how does this actually work that we can do training without these labels? Well, what happens is, even though we have no idea, for example, for this original plane image here, airplane, even though we don't know it's an airplane, or the computer doesn't know it's an airplane because there's no labels, we do know that the two different augmented views both contain the same object, an airplane in this case. Despite the fact it was cropped and rotated, it's still recognizably an airplane. And we call this a positive pair. Two augmented views that have come from the same base image is called a positive pair. And so what we do with our model is we feed through all the different, if we have n images in our data set, we have 2n augmented views. We feed all of them through our encoder. We get a vector representation for all of those images. And then we, essentially with this very complicated looking loss function, but we tell our model to produce representations of the images which maximize the cosine similarity, so the vector overlap between positive pairs, so augmentations that have come from the same base image. And we implicitly as well train our model to minimize overlap of the vectors which come from negative pairs, so augmented views that come from different base images, like a cat and a plane, for example, or really just anything which wasn't from this original image. And what's remarkable about this technique, which when I was told about this by our collaborators, is that you're able to achieve I said before, supervised learning is always the best performance, but you're able to achieve comparable performance without any human labeling. And of course, okay, there's no such thing as, there's no free lunch here. The downside is you need more training time, more training data, and you need bigger and more powerful neural networks. And these type of methods, these self-supervised learning methods, are essentially at the moment limited by the power and the size of the neural networks you can build. So instinctively, this got me thinking about, can quantum neural networks help? And so quantum neural networks might not be a phrase that everyone is familiar with, so I'm going to just introduce that idea. So if you have some familiarity with quantum computing and quantum algorithms, you may have heard about things like Shor's algorithm, which is used the idea is it would crack banking encryption in the future, and Grover's algorithm, which is used for database search. And these are these algorithms invented in the 90s, which showed that quantum computing could really be promising. Now, the problem with those algorithms is firstly, you might need thousands or millions of qubits, which we don't have. But secondly, is that they're not very tolerant to noise. It's kind of like doing a very complicated maths equation or operation. If anything goes wrong along the way, then you're going to get the wrong answer out at the end. And so what researchers in quantum algorithms figured out sort of in the last decade, or maybe a bit less, is that one thing we can do really well or better on real current quantum computers are called variational algorithms. And what it means is essentially it's about solving optimization problems using quantum computers. And so what you do is you actually take a cost function. So in some cases, it could be like, the route for between all your different factories with your logistics, or in other cases, and you encode your cost function into a quantum circuit, right, onto a quantum computer, and you let the parameters, theta or so, the equation of the cost function become parameters of your logic gate in your quantum circuit. So like gamma 1, gamma 2, gamma 4 are all variable parameters in the cost function. And then what you do is, so you essentially use a quantum computer to evaluate what would be, typically you want quite a difficult cost function to evaluate classically. And then you use a classical optimizer to then update all the different parameters to try and minimize or maximize your cost function. So, maximize profit or minimize cost, whatever you're doing. And so these variational algorithms have really become very exciting in quantum algorithm research because they're naturally quite noise resilient. And the main reason is that if you are, let's say, imagine like a well, like a gradient descent, and you're trying to find the bottom of a well. Well, if you go the wrong direction every once in a while, it's totally fine as long as you end up at the bottom. And so basically, the algorithm doesn't rely on any individual iteration of solving the optimization succeeding, because maybe the qubits are very noisy. This is the problem we have now. But rather, as long as on average you're making progress to the solution, then this is okay. And there's sort of another thing which is not really proven, but there's also an idea that by doing optimization in the presence of noise on real quantum computers, you can actually learn some of the noise in the process, but I won't talk about that. And so if I've explained well what variational algorithms are, where you use a quantum computer to solve an optimization with a classical computer as well, Well, then the idea of quantum neural networks is the same thing, essentially. It's these parameterized quantum circuits to solve optimization problems. But when we apply it to a learning problem, like trying to, classify images, then it was recently decided this takes on the name as quantum neural networks. And it does have a lot of similarity in some ways to classical neural networks. And so the structure here, for example, is you have your qubits all in the 0 state, and then you apply some gate, which is going to load in the data that you're trying to classify, let's say. And then you apply a repeated number of layers, which contain your parameters, like your weights, which you're going to try and learn some cost function. And this looks similar to classical neural networks in the sense, that you also have layers of repeated matrices, linear algebra, and that's where it really gets the name from. And kind of what's really exciting is that recently, just numerically, not shown generally, but it has been shown that quantum neural networks can achieve an advantage for very particular learning problems over their classical counterparts. And there's no way to mathematically prove this, just like in deep learning, there's no way to mathematically prove it works. But one idea is, of course, very famously, if you have like n qubits, then the total available, the dimension of the available space to those n qubits is 2 to the power of n. So you have like an exponentially large solution space that you can try to search in. And a lot of work has been made recently into trying to find measures of power which are equivalent between classical and quantum neural networks. And there's a recent paper which says that the effective dimension, which is one such measure, can actually be higher on quantum neural networks than classical. And that's really exciting. And so what we did was we took the SimClear, the contrastive self-supervised learning that I showed you earlier with the different augmentations, and we tried to adapt it to include a quantum neural network as well. And so the end result is the architecture I have in front of you, which is we have the original image, as I said, and the 2 different augmentations. And these are identical neural networks between these 2 different arms. And then firstly, we have a convolutional, a big classical neural network. In this case, it's ResNet 18. And the reason why, we would love to just load the images directly into the quantum computers, but it requires so many logic gates. It's too expensive to do on current, quite small, noisy quantum computers. So we firstly have to have something classical, which is going to take all these pixels and turn it into something smaller. And so the output of this convolutional neural network is then so-called, it's like an initial representation, vector representation of the image. And so then we add into the encoder, we modify the original paper to add a second thing, which we call the representation network. And we call it this, as I said, because it acts on an initial representation. And it's here in this representation network that we actually include either a quantum neural network, as you see at the top here, this is a quantum circuit diagram, or a classical neural network. And that's what we're going to compare between, essentially equally sized, so 8 width, equal number of width, equal layers, versus quantum and classical. And then, as I mentioned before, before we apply the loss function I showed you earlier, we do have a very small second classical neural network. It's only 2 layers, and it's just as an optimization to get better results, essentially. And so, not so interesting, but if people are interested in just the mechanics of how one might go embedding quantum circuits into PyTorch, it's not so bad. And so we use Qiskit, which is IBM's quantum computing framework. I'm very familiar with it. And PyTorch lets you create essentially black box modules. And it doesn't really care what's in this black box, as long as it has a function to call to go forward, so to evaluate the circuit forwards, and also a backward function, which is calculating the gradient of all of your parameters. And they're actually, I'm not going to talk about them, but people have come up with ways to calculate the gradient of parameters on a quantum circuit. And it's actually pretty rudimentary in that you just you shift the parameters up a little bit and shift them down a little bit, and you find the difference and you get a gradient from that. And so this is our architecture for this paper. Now, again, for people who maybe don't have the background, I'm sorry if this is going a bit fast. So what we talk about here is this is the ansatz that we use for our quantum neural network. So I mentioned before, like with the quantum neural network, you're embedding a cost function, but there are many different ways to connect all the different qubits. And actually, you kind of have to guess about what type of gates it is that you want to parameterize here. And so in this case, all of the gates you see here, they actually are parameterized. They have some rotation angle, θ1, θ2, θ3, and so on. And so this is the structure of the quantum circuit and the quantum neural network that we use in this paper. And so what I want to prove to you first is that this thing actually works. It trains. And so we loaded in, we use a CFAR10 dataset, which is sort of just a smaller version of the ImageNet dataset. It's somewhat equivalent. It's also cats and dogs. But just to make it simple to show training, we reduced it just to 2 different classes. So we were left with 10,000 images of aeroplanes or automobiles, cars, you could say. And then what we did is for the representation network, so as I said, this little one here that we are going to use quantum or classical, we used 8 qubits, so 8 width, and 2 repeated layers of this learnable structure. And that gives actually just the quantum neural network only has 32 parameters, which is sort of funny compared to millions normally in classical. And so the first thing I want to show you on this graph is that the loss function, the blue, goes down, which is great, of course. And what this is showing is, as I mentioned before, the goal is to train the network to produce representations where positive pairs, right? So this is a positive pair, 2 augmented views that have come from the same base image, have high overlap, and negative pairs have low overlap. And so this is, by the blue line going down, we can see that, yep, things are training. The quantum neural network is embedded well, it goes forward, and it also calculates gradients correctly going backwards, because the quantum neural network is actually involved in the back propagation process here. And then the other thing I'm going to show is the orange line, and this is called the Hilbert-Schmidt distance. And what you normally talk about it in quantum machine learning is if you were trying to classify 2 different classes, well, the Hilbert-Schmidt distance is a measure of the distance between the classes that you're producing the representations for in quantum space, in Hilbert space. And again, I won't go too much in technical of it because maybe it's not so fun for everyone, but either ask me later or take my word for it that essentially by the orange line going up, what we show here is that even though the loss function acts in the classical space at the end, we measure all the qubits, so it's all classical, the quantum neural network actually learns to also group together these positive pairs in Hilbert space, in quantum space. And that was kind of unexpected for us, but it was a really cool result. And so now that I've shown that training works, we need to find a way to actually quantitatively decide, have we produced a good encoding? Are these vector encodings good encodings of the actual images? And do they group planes together and cars together and cats together? And so the very standard thing to do in the self-supervised learning community is so-called linear probing. And so we train the network, as I mentioned before. And then we freeze the parameters once it's trained, and we add a 1 layer, so like a linear classical neural network to the end of it. And this comes from a theory, which is that if you have found really good vector representations of the images, which faithfully represent the features, a cat has whiskers and planes of wings, then essentially the classes should all be linearly separable in this embedding space that you've created. And so we use a simple linear neural network to try and classify the different classes after training. And so this is really the main result of the paper, which is that we repeat training with the CFAR10 dataset, but this time we make it a little bit harder. So we have 5 out of the 10 possible classes, so 25,000 images per epoch. And what we do is we're comparing now, as I said before, with an 8 width, so 8 wide, and 2 layers of the representation network, right, which is this thing here, and either quantum or classical. Now, in some ways, it's funny because the 8-qubit quantum neural network has access to a 2 to the 8 dimensional space. So it seems like, well, that's a big advantage. But the classical neural network also has many, many more parameters. So it's sort of interesting to see who wins. But the main result we found was that, so this orange line is the quantum neural network evaluated on a state vector simulator. So it means there's no probabilistic noise, which you normally get in quantum mechanics. And the blue line is essentially this is a fully classical model with the classical representation network. And we find that it actually produces better encodings if you run through a quantum neural network, because it ends up being more linearly separable. And the linear probe scores much higher on the prediction accuracy. Even more so, this is 6 repeated runs, even more so than 1 standard deviation. So this was like really exciting for us to see. And essentially the problem is in quantum mechanics is you don't know the exact state of the qubits. You have to measure them repeatedly to build up what the states were. And this is called shots. And so we said, well, okay, physically, even with the world's best quantum computer, you're going to need to do shots. And so we reran it saying on the simulator with only 100 shots per qubit. And still, the results were lowered, but on average, including a quantum neural network in this architecture improves the performance compared to having a classical neural network of the same shape. And so, as I said before, just as a reminder, this is what we're kind of comparing against. This is the classical representation network, the blue line, and this is the quantum embedded into that larger architecture that I showed you. And so the second set of results we have is basically, as I said, there are many different ways to create quantum neural networks. Unlike classical, there's actually many different ways you can connect the qubits and different gates, different rotations you can choose. And we just we picked this top ansatz just as a guess. And then we compared it to another ansatz, which is from the literature, which is supposedly going to be very, theoretically very good for doing learning problems like this. And we were really interested to find that if you change the structure of your quantum neural network, very easily performance can suffer massively. And so here we find that actually it performs the same as, on average, the classical neural network with this second type of structure, despite having the same number of parameters overall. And so this was another interesting result. But of course, what maybe a lot of you are here to think about is, well, what can we do on real quantum computers? And so I should stress that everything I just showed you was done on the simulator. And there's kind of 2 reasons that we do it on the simulator normally. One is that, quantum computers are very noisy at the moment. Quantum states are incredibly fragile, famously, just observing them breaks the quantum state. And so what this really comes down to is that in reality, so qubits have a finite lifetime that they can be held in a quantum state for. And also when you apply the logic gate, so when I tell the quantum computer to apply this gate, this R rotation on the y-axis, it may not actually do it properly just because of imperfections in the hardware. So that's one reason. But actually the main reason we didn't run this on the real device, the full regime, is just because it's like millions and millions of quantum circuits. And even though these only take a second each, it adds up. And no one, we didn't have access to a quantum computer for several weeks at a time. But what we did do is we thought, okay, what can we do on the real device to show how good they are at the moment, if they are good? And so what we do is we train the network fully, and we do the linear probing. So we essentially have a network that is good at classifying these images from self-supervised learning. And then we feed in new images that it's never seen before. And we try and classify those new images using the real quantum computer here built into the algorithm. And so in this case, we use the IBM Q Paris, which is one of IBM's quantum computer. And it's actually 27 qubits, which is an overkill because we're only doing 8 qubits, but yeah. And again, a sort of technicality for those who maybe are interested or more in sort of research level, one thing we have to do is to really minimize the amount of noise on the real quantum computer. We use a recompilation algorithm that we developed in a different work to mean that you use the minimal possible number of logic gates to do your quantum neural network. And similarly, you'll notice here that the qubits on the physical device are not connected in the same way. They're connected in these rings. That's not the same way as these type of connections necessarily. So we also needed to recompile it for the different, accounting for the different connections. And so the end result of taking these pre-trained models and classifying either new images on a fully classical setup or a classical quantum hybrid setup with a real quantum computer is that they actually come out at almost exactly the same overall accuracy, very close. So despite the fact that there's a lot of noise on the quantum device, the theoretical advantage that I showed you earlier on the simulator is enough to offset this. such that you end up tying on predicting unseen images. And actually, in some of the cases, it actually, for particular classes, the quantum computer performs better. Okay, so I wasn't lying. Like I said, the talk is only 20 to 30 minutes and hopefully plenty of time for questions. So what do we do here? Well, really, hopefully I introduced the concept of quantum neural networks. And basically, quantum neural networks so far have only really been applied to supervised learning or to sort of quite simple data sets that were 40, 50 years ago. And we really wanted to ask the question of, could you incorporate quantum neural networks into a cutting edge modern computer vision algorithm? And the answer, okay, you can. And actually, even better, it's a slightly artificial test because you wouldn't really have this big convolunet and then a small one. But we just asked the question, if you included a second smaller neural network in the architecture, would it be better if that's quantum or classical? And actually, the answer is quantum, which is awesome. And again, as I just showed you, despite the fact that the real quantum computers are very noisy, if you have a few clever tricks and stuff, we're able to classify unseen images on the real device with equal accuracy to classical. Now, I say outlook, or maybe just sort of a few drawbacks I want to raise. The first thing to ask is this really a fair comparison? And so we're comparing the power of 8-qubit quantum neural networks to 8-width classical neural networks. So as I said before, quantum neural network has access to a 2 to the 8 dimensional space, where the classical only to 8-dimensional space. But the important thing is we chose a very hard problem on purpose because it's not obvious, particularly after so much pre-processing from the classical convolutional network. It's not obvious that you would need that extra dimensionality. And for all the drawbacks of using quantum, like having far fewer parameters, we still saw an advantage from the extra dimensionality, and that's really cool. But these type of algorithms, these variational quantum algorithms, no one really knows how they're going to scale to 50, 100, a million qubits. And this is very much an open question of, could you do this? Ideally, we wouldn't do 8. We would do the biggest possible quantum versus the biggest possible classical, and we'd compare them. And but one exciting thing about our scheme is that we don't have to actually just classify classical data like images, like I showed you. And no one has really done this yet, but one could take the idea of self-supervised learning and apply it to quantum data. So for example, quantum phases of matter. And you could try to classify or predict, for example, given a quantum state, what phase of matter is it in? What phase of it is it in? And this could be done if we essentially turned our architecture I showed you and did it all quantum rather than classical then quantum. And so, yep, just of course a thank you, an acknowledgement to the people who helped me a lot. My supervisor, who's Diti Aksh at the University of Oxford, and then Lewis and Martin, who are in my group, who are also quantum researchers, and Whitey and Sam, who are they're not quantum at all, they're in the visual geometry group doing computer vision, and they collaborated very nicely with us. And okay, here's a shameless plug for myself. If you're interested in what I'm talking about and so on, I'm on Twitter. That's the main place you can follow me. So thank you very much for listening, and hopefully we have plenty of time for questions if there are any.
Yes, thank you very much, Ben. It was a wonderful lecture, and we have several questions on our chat. So let me maybe just read the first question. Can this method be used in gene sequence analysis? I mean, sequencing genes.
I have to say, I definitely don't know enough about gene sequencing analysis to know the answer exactly to that. And if by what they mean this method is this idea of doing these, like, not knowing what your data point is, but doing the augmentations and knowing that both augmentations come from the same object.
Exactly.
Something. Sorry, is that correct?
Exactly. That's what I mean by the question.
Yeah.
That was the time I asked the question.
Great. So yeah, I don't know about that particular area. I don't know much about that area, but what I would say is it's applicable to any area so long as, and this is like where the clever bit is, the human intervention. You just need to make sure that your augmentations that you apply don't change the fundamental meaning of whatever you're trying to classify. So for example, you saw we did cropping and rotating, but a plane is still recognizably a plane. And if you were to apply it, you don't have to have images. People have used these techniques on just vectors, just pure data, for example. but maybe you augment the data in a way which, as long as it doesn't change what you're trying to classify, it should be possible. And people have, I have a citation in the article, I can find it for you. People have applied self-supervised learning to computational biology. I just forgot where exactly.
Mm-hmm. Okay.
Can I be a bit more specific in my question?
Sure.
There's some technology or technique called CRISPR that changes the gene structure of a person, okay, and that's therapeutic. But the point is, maybe your augmentation and what you describe as unsupervised or self something, that new method can help to find out, to identify where to do it, okay, in the gene sequence to do the change, the CRISPR, which is basically cutting some part of the sequence.
I
So
think
if you can guide me where to do it, that's a big deal.
Yeah, for sure. It sounds like a great idea. I think that I've heard of CRISPR. I wouldn't really know how to do what you're talking about. And I think the main thing I would say is you have to ask yourself, like, it is a way, it's a method to learn representations which group together like similar things. So if you want to do some sort of classification later, that would be really useful. In terms of like where to edit a gene, it sounds more like some type of evolutionary algorithm to me, where you try lots of different outcomes rather than this method. But maybe there is something that I don't see, but I'm just not familiar with those type of techniques.
Okay, thanks. Mm-hmm. Very promising.
All right. I can see that Karim also sent a reply on chat, so maybe Karim, would you like to add something? I'm not sure if you can hear us now.
I'm sorry, I was talking about why my mic was muted. Actually, no, I think Ben has answered the same answer that I would give. So,
okay, great, fantastic. All right, there's a question. Next question from Aisha. Noor, what's the role of the projection head? I think it was explained during the lecture, but maybe you
No, I did skip over a bit, so that's good that someone asked. So essentially, if you're really interested, I'm just going to jump through the slides. This it is explained. So this is the original citation at the bottom of the original classical algorithm. So the role of the projection head is a funny one, which is this type of loss function. It's called a cross XTNT, cross temperature entropy loss function. And they found during experimentation that if you apply this directly on the final layer of your neural network, so let's say you didn't have the projection head, let's say you just have the encoder, which is actually what we do in the linear probing, then it leads to, how would I say that? I can't remember what the phrasing they use. It leads to a loss of information on the encoding, essentially. Like a lot of the thing in deep learning, I guess it was like I think they tried the algorithm first, and then they tried, it's kind of trial and error, and they added on a projection head, and they found this improved it. And there's not a very strong theoretical reason why, but it seems that the loss function induces loss of information on the final layer. So you actually want to have an extra layer at the end. But it's interesting because when you do the linear probing, you get rid of the projection head. You just look at these yi. So these truly are the representations. But in the learning process, you add on the projection head. I know that wasn't a very satisfying answer because I just answered it by saying, well, that's how it is. But really, that's the level of at least my understanding. And they talk about it a little bit in the original paper. And there's been future works actually where people have tried putting like 5 projection heads in and got even better results. So I think a lot of deep learning is that type of trial and error.
All right, perfect. Thank you very much for the answer. The next question, interesting. What does it mean that there is learning in the Hilbert space?
Yeah, this is a good question. I'll jump to the relevant slide. So it could mean a lot or it could mean nothing. I've also thought about this, like, it's very easy to overinterpret certain results. I would say that, it's possible that because the quantum layer is in the middle of the architecture, it was very much possible that actually in the quantum space, you're not doing this type of overlap. You're just preparing representations which the next classical layer will suddenly make into a very effective representations with high overlap between positive pairs. But yeah, I think what it means is that essentially even though we measure the qubits and we're not classifying in a quantum space, we're classifying in a classical space, there is a correlation, there is a correspondence between separating or grouping things in a classical space and separating and grouping them in the 2 to the n, the exponentially larger quantum space. And it's promising, okay, what it does mean is that you could do a fully quantum version of this algorithm, which isn't so obvious before this work, because yeah, sometimes it's not clear whether in many cases in quantum algorithms, the Hilbert space is too large and you lose the signal. But so I don't know if there's like a deep meaning to it, but it does mean you could do like fully quantum self-supervised learning and not have to, in the future when we have 1 million qubits, and that would be really cool. Does that answer your question? I don't know who asked it.
Yeah, I hope so. In my opinion, it's fair enough. So maybe there will be some follow-up questions later. But there's another question regarding this Hilbert-Schmidt distance. So this Hilbert-Schmidt distance was increasing during the training process.
Yeah.
But you said that it shows that the classes are being separated. Can you expand on that about it's usually points in the same class should be close to each other? So there should be
absolutely. So I see a few more in the chat about that. So that's my fault for skipping over it. It's come back to bite me, but I can explain it now. So what these terms are essentially is in our case, okay, so often you have a quantum neural network, and let's say you have only 2 classes. So let's say whenever you feed a class, an image belonging to class 1, this becomes the state vector that comes out the quantum neural network is this like psi I belonging to rho I. And so the rho and sigma normally in like the paper we got it from, which is the Sesloyd paper in citation 10, the rho and sigma are a statistical ensemble, which is like averaging the state vectors of all of the states produced by the different images in each class. So you can imagine like in a Bloch sphere, in a Hilbert space, this rho I is like the average position of all state vectors belonging to class A. And the sigma I is the average position of all state vectors belonging to class B. And so the Hilbert-Schmidt distance is essentially a measure. When you do this, expand this quadratic, you have 3 different terms. One is how clustered is rho I. So this is the rho squared term. And that like maps how well your model maps the same classes, images of the same class into the same state vector. And then you end up with this rho sigma term, which is the distance between the average position of state vectors of class 1 and the average position of state vectors in class 2. So now in our case, we adapted it slightly. So for example, let's take a positive pair. I showed you like the cats or the aeroplanes. For a positive pair, we run those 2 images through our quantum neural network. And this is what these state vectors are here. So psi I1 is one of the images, the states made into a matrix, and then psi I2 is the other one. And so rho I is like the average position in quantum space of the positive pair. And then sigma I, what you see here is we sum over all the other images that aren't part of this positive pair. So it's literally, just 2n minus 2 images. And we sum the average position of those. And so by doing this Hilbert-Schmidt distance, we're measuring, by doing the rho minus sigma, we're measuring the average distance between a positive pair and all other images. And so we're able to, if that increases, what it's showing is that positive pairs are getting grouped together and they're getting grouped away from things that aren't from the same base image. And then just to make it even one more step confusing, we then do this for every positive pair and we average all of those. So the orange line you're seeing is like the average separation between all positive pairs and their surroundings. And so by it going up, we can essentially show that this distance is increasing in Hilbert space.
Perfect. Thank you for this very nice explanation, very detailed. And there's the next question. What's the average walk-up time for an entire training run? Is it substantially faster than classical training?
Not at all. So that's a great question. So, one of the issues we have here is all of this work, the bulk of the work we do is on the simulator. And simulating quantum circuits is like much more expensive than running classical neural networks, both fundamentally, but also because classical neural networks have had decades of efficiency improvements, and they're running extremely efficiently on GPUs. Whereas like quantum circuit simulation is only just starting people talking about, can we get it faster on GPUs? And it's massively behind in technology. So for the pure simulations of these, so if I actually show you, if I go ahead, the orange and purple lines took about 5 days to get, and the blue line takes about 10 minutes. And you might say, well, doesn't this just invalidate everything you've said? How is it better? But the point is that in the future, the idea is, running on real quantum computers, gate times are, nanoseconds. The qubit lifetimes can live longer. And so at that point, that's the question to start asking, comparing the run times between running on a real quantum computer, which doesn't have to simulate it, it just does it naturally, and the classical. But yeah, there's no way at the moment that classically emulating these quantum networks will be better, because it does take, a factor of 1,000 longer at the moment. But that's because of the difficulty of simulating them, essentially.
Mm-hmm. Great, thanks for this answer. The next question, in the training batches, can we cluster further to reduce noise in distributed computing, more specific for edge devices?
Sorry, can you say that again?
Yes, so maybe I will just read once again. Is the training batches, I think that it should be maybe in the training batches, can we cluster further to reduce noise in distributed computing, more specific for edge devices? I'm not sure, maybe because this is a question posted by Jayakar, Joseph Johnson, so maybe the author can clarify more. So there's the follow-up information that may combine with self-supervised learning for scaling, but maybe the author, Jayakar, can.
Yeah, I'd appreciate that. Sorry, I don't.
For me, it's also not obvious. So.
Oh, sorry, I've just clicked on the other. Yes, I was looking through the chat.
Yeah, that's fine. If not, so maybe Jayakar. Okay, so I think that Jayakar is now unmuted. So.
Yeah.
Yeah, go on.
Yeah, that's it.
So could you mind explaining your question a bit more? I just don't understand what you mean about, so in the training batches, can it be distributed?
Can
yeah, that is it. See, that I brief about the application for the cancer treatment, that there will be a lot of devices to be connected across that metastasis. So this data image processing data that we plan to have with that deep neural network. So that will have layers.
Okay.
So that's why that self-supervised learning along with that is the quantum self-learning. If we combine both, that is the from different locations the data can be that. That's why that we are looking for that.
Okay. I still think that I'm not like fully on board, but in terms of the applications to like cancer treatment and stuff, this is like one of the really promising areas of self-supervised learning, because you can totally imagine, for example, taking an X-ray of someone's lung, and you can modify that in loads of ways, which doesn't change the fact that there is a tumor somewhere. You could flip it, you could do all sorts. So that's a really, you could take, again, millions of images of cancer patients and not have to have someone labeling it, and do the same technique. And as we showed here, even for image data, if you firstly process it classically and then use quantum, then hopefully it can help. I'm sorry, I hope that answers your question. Yeah. I'm sorry if I didn't fully understand it.
Yeah. Before image processing, the signal processing stage itself, the data has to be segregated.
Oh, I see. Yeah, I mean, yes. You don't have to have an image come in. You could have a vector. You could have any pre-processing you want, essentially. It's not an issue. Yeah.
Thank you.
Okay,
Thank
thank
My
you.
pleasure.
Shall
My pleasure.
contact you. Right.
Okay, great, perfect. There's another question from Dev Sharma. Is it a type of reinforcement? I guess that's reinforcement learning. So I guess we cannot probably classify self-supervised learning as a part of reinforcement learning. How do you think, Ben?
Yeah, I would agree, right? So I've only got into deep learning in the last year, so forgive me, but if I don't know well. But I guess reinforcement learning, typically you're talking about, is this right? That it's you kind of take step by step, you make decisions. So like if you're trying to teach an agent to learn how to play chess, this is reinforcement learning because you take a decision and then based on the decisions you have to take the next one. And now that was a terrible explanation, but no, this is not reinforcement learning. This is
this is something else, right?
Exactly. It's more about classification. Yeah.
Yes. Yeah. So in the slide title training, can you give a brief description of rho I and sigma I? What are the significance of these two terms?
So yeah, hopefully I saw that question before. Hopefully I explained it. I can do it again, particularly with those terms if we want.
Excuse me. Yeah,
Oh,
I was the one who asked the question before that regarding the the explanation for the distance and the tuning. So it was supposed to be a follow-up question, but it was answered perfectly during
Good.
that.
So did that help? You understand it now?
Yeah. Very
great.
Absolutely.
Good.
Thank you very much.
My pleasure. And I think someone linked the original paper, the Seth Lloyd paper, which does talk about that idea of Hilbert-Schmidt distance. Great.
Thank you.
All right. Thank you. There's another question regarding self-supervised learning in general, I guess. So as human is not involved in labeling the data set here, how is it taken care?
How is it they can what, sorry?
How is it taken care? So how the labels are generated. So I guess that this was just the essence of this lecture, right? So how to generate these labels without human.
Yes, I can talk about that briefly again, if that's helpful.
Sure.
So yeah, it's a really cool idea, but even though it's not labeled, so like if I was the model and I get an image in and I have no idea what is in that image, but what we as humans have done is we've constructed a set of augmentations that can be applied randomly, but which still won't change the semantic meaning of the image. Like, in this case, it's recognized to be an airplane in both. Well, this works really well because it means that the model doesn't need to know that it's an image, that it's an airplane, as long as it knows that the two different augmented views do belong to the same class. And that is the absolute essence of this type of training, which is that, so even if I look at the loss function, I can just explain to you that this term on the top, Zi1, Zi2, right? This is like Zi1, Zi2, both come from the base image Xi. So we basically are training to produce representations which maximize the overlap of the vectors of the positive pair, the two augmentations that come from the same class, despite the fact that we had no idea there was an airplane inside. And implicitly, we minimize everything else. And that actually is funny because you do get a lot of false negatives. So there might be another picture of a plane, but because the augmented views didn't come from the same exact image, we actually might tell the model sometimes to minimize between a plane and a plane. But on average, you're training in the correct direction because you are also saying to produce overlap between the two positive pairs. I hope that makes sense.
Yeah, I think this was a very good answer. So thank you, Ben. All right, there was maybe one more posts regarding this Hilbert-Schmidt distance, but I think that was just a comment to your answers, that this answer clarified the essence of this Hilbert-Schmidt distance, and it seems that it functions like the quantum version of the triplet laws. So it minimizes distance between positive pairs, maximizes distance between negative pairs. So
yeah, I think the Hilbert-Schmidt distance itself doesn't minimize and maximize, right? It's just a measure of the average distance between, in our case, positive pairs, just two classes. And in our case, we choose the pseudo classes, which are positive pair and all other images. But you could equally pick, in supervised case, cats and dogs, the distance in Hilbert space. But yeah, this is what they do in this paper. You could explicitly optimize, not for this loss function, but you could make a quantum self-supervised learning and optimize explicitly for the Hilbert-Schmidt distance. And that would be interesting, because then maybe, yeah, then it is responsible for maximizing and minimizing the overlap of positive pairs. That would be a cool thing to try.
Okay, great, fantastic. All right. There was also just maybe one reply, one information regarding Hilbert-Schmidt distance, that it is in the higher dimensional tensor product space. So this is the comment from George.
Precisely, yeah. When I say quantum space, Hilbert space, it means that, 8 qubits is 2 to the 8 dimensional space.
Okay, great, fantastic. I see some posts from Karim with links to. There is one link to the paper explaining this Hilbert-Schmidt distance and also this rho and sigma parameters, and also there is a link to the paper Quantum Self-Supervised Learning. So thanks, Karim.
Thank you very much.
Yeah, are there any more questions or comments?
Yes, I have two.
Go on. Okay, go on.
The first one is talking about the ansatz. Like you compared 2 ansatz that you found in the literature, and they showed some promise, right? Some improvement. And the question is, do we understand the ansatz as a trick or some elegant way to define something that later on shows up some progress, some advance? And if so, maybe there are more ansatz, or we can invent another ansatz.
Absolutely. So I'll answer your first question first now. So totally, like this is a lot of the research done at the moment in variational algorithms is about the ansatz. And from a physicist, from my perspective, this seemed fine. And then I spoke to for example, my collaborators in the computer vision department, engineering department in Oxford. They were so shocked that, quantum computing researchers haven't figured out yet what the best ansatz is, and obviously it's different for different problems. But at the moment, it is a bit of guesswork. What we took this first ansatz from, the so-called ring ansatz, we took it from a paper where they just start now looking numerically at concepts that might give you a good ansatz. So things like expressibility is what it's called, where that says how much of the whole Hilbert space can my ansatz cover. And then the idea of entangling capability, which is, we know that you want high levels of entanglement to do things that are difficult classically.
Right.
And so you're right. So I show here that we kind of just chose 2 other literature, and they happen to have like quite different performance. One is classical level and one is better than classical. And the suggestion we got was, to start looking at more like actual algorithms to find the best ansatz for a given problem. In classical neural networks, they have this thing called DARTs. It's differentiable architecture search. And this is actually something they use. And just like a few months ago, someone did a quantum version, slowly starting to copy the classical neural network guys about how we find good ansatzes. So it's a great question.
Excellent. So just on this one, before I go to the next question.
Sure.
If I look at these pictures and I don't know anything about the deep content or the wisdom of ansatz, I can compare these 2 pictures and play with all these gates, if these are gates, and come up with a configuration just by moving and shifting things and adding things here, and it may turn out to be the better ansatz.
Absolutely. And
is this very naive or very silly?
No, like this is totally right. And after we did this project, so in this case, because it's quite a long time to run each line, but yeah, we could do another work where we could do 20 different ansatzes and just see what performs best. And I actually thought, well, even you could go a step back and just do supervised learning on MNIST, for example, like people did in quantum a few years ago. No one's done, okay, here's 20 different ansatzes, which one performs best on supervised learning of MNIST and why? And I think that I suggested it as a project to some people in our group, and in the community, it's seen almost as like, oh, it's a bit boring. It's engineering. It's kind of just a software. It's not fundamental physics. But I really think this is like we have to answer this question to get the best results on near-term quantum computers. And I think the trick is that the answer is going to be different for every different type of algorithm. Maybe hopefully there's some sort of general overview, like high entanglement, as I said, high expressibility, but maybe, yeah, like on this graph, it's on these diagrams, it's not obvious that these should perform differently. They have quite similar structures, and this actually one has more entanglement. So yeah, no, it's not naive. This is a totally fair point, and that's where the field is. We haven't got that far yet.
Okay, sounds great. So now I have a last comment question.
Mm-hmm.
Can I use this approach to deal with something very problematic, which is called cybersecurity?
What would you imagine you're trying to
Well, in
group or
cybersecurity,
classify?
I'm looking after some unknown sources of intruders.
Mm-hmm.
But they leave their signatures somehow in,
Yeah.
I can collect some data about the damage they do. I can collect, you know, maybe it's not perfect information about them, of course, but it could be that these strong tools here can be useful.
So I think that's a good example. I think there's an interesting question there, which is whether you would use this or just use normal supervised learning. So it depends. If you have
all of them, I would use all of them. I tell you why.
So, but as I was saying at the beginning, it's like the big reason you might do this is if your data set is so large that annotating becomes really problematic. Now, I don't know about cybersecurity. I would imagine that, I guess, I don't know, but maybe there's only a handful for a given company. There's only a handful of breaches, or maybe there are 1,000 breaches a day. I mean, I don't know. But if it's small enough that you could manually label this is an intruder and this wasn't, then you'll always get the best accuracy from supervised methods. But if you have like aggregating, I guess, over entire, I don't know, thousands of companies, and then you have millions of examples of intruders versus not, then yeah, this might be a technique. If you can find a way to, as you say, they leave a signature, they leave a fingerprint. If you can find a way to alter the signature which doesn't affect the fundamental meaning, just like I was saying with the images, then yeah, potentially.
Okay, great.
Okay, so regarding this last question about application in cybersecurity, there was maybe an interesting comment from Barry that maybe we can just use this technique to distinguish spam from legit emails. So that sounds to be reasonable, but we'll see. So there is another comment, a question from NJ Todd. I would be interested in that study on ansatz effectiveness. Had you done only all in all, this would have been a very different paper.
Yeah, it really would have. Maybe I can actually just, I want to, if people are interested in ansatz effectiveness, I do want to then, maybe I can share this paper where we took this ansatz from. This is called Expressibility and Entangling Capability of Parameterized Quantum Circuits for Hybrid Quantum Classical Algorithms. And they almost do what I want. They don't go as far as to actually try each one on a problem, but they talk about these theoretical ideas, expressibility, entangling capability, and they plot them all differently. And it's funny that we took a ansatz from their paper and it did really well. And we took an ansatz from a different paper, which was just like, this is just the only ansatz they tried. And that also, it was in quantum neural networks, and that all-to-all ansatz did really well in that paper, but on our problem it didn't. And as you say, it would be a really different paper. I guess we would have tried a different ansatz maybe, but in some ways we got lucky, and in some ways, yeah, who knows?
Okay, thank you, Ben. There are two more questions posted by Karim. So first, can you please explain more the ISL approach for circuit compilation and creating low-depth, high-fidelity circuits?
Great, yeah, good question. This is one of those ones where, as a researcher, you plant extra slides and you're hoping someone asks. So now I have slides to show you. So just as a reminder for what I was saying to everyone, so like when we want to get the most performance out of near-term quantum computers, we need to use the least amount of logic gates in our circuit. And the reason why is like the fidelity, let's say, of this quantum computer, in some of them, let's say it's 99.9%. which sounds really high. Like for every gate, there's a 99.9% chance it succeeds. But as you add more gates, right, the overall chance of failure or of not doing what you want grows exponentially. It's 0.999 to the power of the number of gates is your overall chance of succeeding. And if that is 1,000 gates, then this is like a 0% probability you're going to do what you intend. And so we developed this thing called ISL. I'll jump through. So it comes from an idea which I didn't come up with. Simon Benjamin at Oxford is one of the people who came up with the idea. But let's say I want to take a gate, a unitary U on the left, and I want to recompile it into some approximate similar set of gates, V, but which are much shallower. Well, the one way to do it is to prepare your qubits in the 0 state, and then apply the U which you're trying to recompile, and then start trying to find the inverse, which will give you the 0 state back. So start actually adding gates and seeing if you can get back to 0, 0, 0, 0. And then if you have, then you can just do the inverse of V to the -1 and you can get V. And so we came up with this algorithm. It's on a previous paper. I only have 2 papers, so you can see the previous one. We did it for a quantum chemistry problem to get the maximum performance on the near-term devices, called incremental structural learning. And it's a bit like the ansatses. It's like we didn't want to assume we know the structure of this V to the -1. And so instead what we do, because, okay, if the qubits start in the 0, 0, 0 state, and we want them to end in that state, this is a totally unentangled state. We call it a product state. And so we actually know that we want to remove entanglement from the qubits. And so what we do is we actually find the first step of ISL is like you find the pair of qubits which have the highest entanglement. And there are many measures of entanglement, but we use a particular one. And in between those qubits, you add this set of gates. So a C0 surrounded by 4 single qubit rotations that have undefined so far both axes and angle. And then what we do is we actually then optimize all of these axes and angles with respect to getting the highest overlap between the output and the 0, 0, 0 state. And so here is a GIF of this actually working, where the cost function is the overlap between the output of what this does after the U and the 0, 0 state. And so what you find here is that through some set of iterations, we can actually learn to go back to the 0 state, and then we do the inverse and we find an approximate shallower state. And I don't have the slides here, but so on the previous project, we found that you could have circuits of thousands of gates, and they can be approximated to 99.999% using 10 gates, just with this structure. And so like I just try to use it in all the work we do because it gets so much more performance out of the real devices. What I would say is it's not, you can never get the exact state. It's not like there are redundant gates, but you get it to 99.99%. And this is good enough if your noise is really high anyway.
Okay, might I ask another question?
Yep, please.
Yeah, sure, go on, Karim. Mm-hmm.
Okay, so how, like in the learning process, we have like the basic network for creating the embeddings and then the projection, and after that calculating the loss. So you are using a quantum ansatz to create the embeddings themselves. Okay, how do you inject the ISL approach inside this learning process?
Yeah, it's a good question. So it's funny, we don't actually do it in training because as I was showing on these slides, so to use a real device, we totally train this to completion normally on the simulator. And so the quantum neural network is no longer a bunch of parameters. It's a bunch of like fixed values. So it's like a fixed circuit. But you're right, for every image that we pass in, which becomes a vector, it's actually going to be like a circuit, but with a different set of initial gates to load in the vector. So for every single image, we had to run ISL. And then from that, we get an approximate shorter one. And then we actually just run that on the real device. And it will give you, the same vector out that we would have got if we'd run the full neural network. And so that's how we incorporated it. You could incorporate it into the learning process, but it would be a lot more, you'd have to do it many, many more times, because when you're learning, for example, yeah, when you're learning, you also do the gradient calculations and you have to have many, many more circuit evaluations.
Yeah.
So it's actually particularly good in this case where you have a fixed circuit that you know you want to run on a real device.
Okay, thank you for this clarification. Is there like a published code for the ISL approach, or
Is there a GitHub, did you say, or a code?
yeah, is it on
Yeah.
GitHub?
So I think we recently made it public. Yeah, it's the steps to this is in this paper I've got at the bottom here in this other paper. If you want to look at the actual steps, we're in the process of writing a paper just for ISL, but it's just taking a while. Let me just check with the other author that it is public, and if it is so, then maybe I can just send me a message on Twitter or something. I can give you the repository. I just don't want to do it in case it's not meant to be public.
Okay, no problem.
Cool.
I have another question. So right now we have like a pair of images, and then we feed it into a convolutional layer. So that you then feed it one more time to a quantum ansatz. Is that correct? Or the quantum ansatz actually replaces the convolutional layer?
No, so you're exactly right in the first case. I wish the quantum ansatz replaced the convolutional layer, but because we can only simulate like, maybe at best 20 qubits, and it's expensive, you just said simulating a few million circuits took 5 days. Basically, we wouldn't have enough power. We wouldn't have enough, like, you need like 1 million parameters to do this stuff, right?
Yeah.
So what we had to do is, the convnet comes first, and then actually it's a slight subtlety I didn't mention. The output of the convnet is a 512 length vector. And then we have one more linear classical neural network layer to go from 512 down to the number of qubits. So it's like a compression.
Yeah, okay.
And
no, I understand you now.
I actually have, again, a slide for this, but just for example, in a purely classical case, so as I showed you, it's a quantum ansatz or a classical. This is what happens when you compress to different widths. So like you can see in like the 2 case, it doesn't really learn at all. And so we picked the 8 qubits because this was the narrowest, so the cheapest to simulate, where the performance still held, the performance still improved over a long training time, essentially. So it wasn't so compressed that you lost the information used to do the classification, basically.
Okay. What is the backbone of the convolutional layer? Is it like a ResNet?
It's ResNet 18, yeah.
Okay, that's great. One last question. Regarding calculating the loss, have you considered using a swap test for the projection heads?
So this is a great question. So if we were, so as you see, when we do training, because we have the projection head, we actually basically measure all the qubits. So it actually, I showed you the Hilbert-Schmidt distance, right? But then actually what we do is we measure all the qubits, get a purely classical 8 length vector again, and that goes into the projection head. Where's the projection head? There. And then that goes into a thing. So we don't need to do like a swap test to get the state, the quantum state, because we actually do the loss function in a classical space once we've measured all the qubits. But if you want to do fully quantum self-supervised learning, you're absolutely right. Like you would probably want to not measure the qubits because you'd lose the dimensionality, and maybe do some sort of swap test for the loss function. That's a good point.
Okay, thank you so much.
My pleasure.
All right, thank you, Ben, and thanks, Karin, for great questions as well. Do we have any more questions? I don't see more questions on our chat now, but
Good.
maybe someone
looks like
would
we've
like
exhausted.
to...
Yeah.
Yes. Yeah.
We've exhausted everyone, but if people have more questions, just ask now. I still have time.
Discussion part was maybe even longer than the lecture, but it was really
I like that.
Great. It was fantastic. So maybe just a follow-up question regarding this code repository, and maybe this will be the last question. So you mentioned that you developed this Qiskit library, right, to just run these quantum neural networks using Qiskit. So is it the same code that you had in mind while just answering Karim's question about this ISL, or
different? So I'll tell you what's available. So about you can see my whole browser, right? So I can show you here. So so this is the code for just basically it's mostly just PyTorch code with then like I showed you the architecture with our quantum neural network stuck in. So this is what you can run. You can run these commands to get, it takes like a while, but to get the results we had. But then we made our own library, which is also public, which I just called Quantum Neural Network Unimaginatively. And this is for you doing quantum neural networks in Qiskit. So this is actually public. And this is, if you use the link, I think they're going to email the link to the quantum self-supervised learning repository, you can find it because it's a requirement to run the quantum representation network. You need to also clone this and put it on your sys path. And then, so this is publicly available, and we only ask that if you use a paper, you cite the work. So that's all available. The ISL stuff might not be, but I think it's meant to be. So I'll get back to everyone on that.
All right, perfect. Yeah, so Helen also replied on our chat that she will email these GitHub links upon request, but maybe they can also be sent and or published on our website of this event on meetup.com. So thanks Helen for this as well. All right, are there any more questions to Ben? I think it's the last chance to ask. There are no more questions, just a comment that it was an excellent presentation, and we all thank you, and I think that everyone can agree. And so this was really great lecture, so thank you very much, Ben, once again. Yeah, I think we can finish for today.